pleasure.
Thank you very much. What can I say? Thank you very much for that very kind introduction. So, have we got our slides at this point? And, oops, let me back up one. Yes, there we go. So, medical nanorobots and their development. So before I start, I'd like to say there are a few websites. I'll be able to provide just enough information, I hope, to tease you and make you say, oh, that sounds interesting. And then if you'll remember these websites, you can go and find further information. The first one is discusses nanofactories, what they are, how they might be developed. And the second one discusses nanomedicine, what it is, what the various possibilities are. And between them, they cover a fair amount of turf. And then, of course, you can always wander around with Google, which is a delightful way to spend actually a very long period of time. So what am I talking about? Essentially, I'm talking about things that we care about, health and wealth, and how those things that we care about relate to atoms. And in the upper left, you see a picture of coal, and in the upper middle, you see a diamond. Well, those are the same element, and it's carbon in both cases, but the arrangement has been changed, and we place a higher value on the diamond than we do on the coal. In the left, the lower left, you'll see a computer chip on a pile of sand, and again, it's the same elements. If you take sand and add a pinch of impurities and rearrange the atoms, you get computer chips. So again, how the atoms are arranged is very important. And then, of course, for health purposes, the major question, the major issue of importance is how the atoms are arranged in you and me. Someone who is healthy in the bottom middle, someone who's unhealthy in the bottom middle in a hospital has atoms that are arranged in a way which is perhaps not optimal, whereas someone who's healthy on the right is out bicycling, having a good time. And again, the fundamental difference is how the atoms are arranged. Well, okay, that's very nice. Do we have tools for arranging atoms? And of course, we have the vast array of technologies that have been developed by chemistry, but what I'd like to focus on are some newer techniques that look like they have a great deal of promise and which looks like they can provide a more direct path to arranging and rearranging atoms. And in particular, we've seen experimentally the demonstration of atoms being arranged on surfaces. Here, we're looking at silicon atoms being arranged on a surface, and in fact, they're being arranged with such control that you can actually spell out specific letters, SI in this particular case, in the lower right-hand corner. Now, the reason I picked this particular one, by the way, every year when I give the talk, I take whatever the latest and most dramatic research is in terms of arranging atoms on surfaces. The reason I picked this one is that this is done at room temperature rather than in liquid helium or at some very low temperature. So we're now seeing a demonstration of arranging atoms at ordinary temperatures. We're seeing the making and breaking of bonds. In order to make those arrangements that you see, the experimentalist actually had to take a probe tip and touch it to the surface and make and break bonds in a relatively controlled way, and as a consequence, spell out the particular initials, SI, which you see in the bottom right, and which demonstrate very precise control. So we're now at the point where we actually can make and break bonds at room temperature. We're still confined to the surface. So if you look, you'll find excellent experimental demonstrations of arrangements of atoms on surfaces. You will not find people using this kind of technique to build three-dimensional structures. So we now have to move into 3 dimensions, and hopefully that will be coming in the next few years. So moving beyond the experimental demonstration, the next question is, well, how could we move into 3 dimensions? If we wanted to build complex structures that extended into 3 dimensions, how would we do it? Well, if you're using as inspiration the ability of a scanning probe microscope to probe and move individual atoms, then you might say, well, let's go ahead and use some sort of probe technique, some sort of positional technique, and let's use positional tools, very precise molecular tools, and have them interact with a structure so that you can build it. And the obvious question, if you propose that as an objective, is, well, what do the tools look like? So here we see a paper that was done a year or two ago now, which describes 9 theoretical tools. And what you're looking at, of course, is the very tip. So in other words, we'll have a larger structure that will hold the particular arrangement of atoms shown at the very tip. And the very tip can be analyzed theoretically. The tip can be modeled computationally using your favorite computational chemistry package. And you can see what the tools could do. And after looking at this particular set of tools and analyzing it, we see hydrogen, carbon, and germanium atoms involved here. We find that if you look at it and think about it and do enough work, and there's a nice detailed paper that discusses all of the reactions involved, you can use that set of tools to make another set of tools, which is a good basic property if you want to have molecular machines that can make more similar molecular machines. You can use those molecular tools to recharge that full set of molecular tools. And you can also use that set of molecular tools to make a wide range of nanorobotic devices. So that set of tools, which has been analyzed theoretically but not yet demonstrated experimentally, should allow us to build a wide range of interesting structures. Here's a particular structure. Again, this is a theoretical structure. This is a hydrocarbon bearing. It involves a shaft, which is diamond wrapped into a tube, and the shaft is inserted into a sleeve, and the sleeve is another flat sheet of diamond bent into a tube. It's kind of interesting. At the molecular scale, diamond is slippery, flexible stuff. So the idea of bending diamond is feasible if you've got a thin enough sheet of diamond. And these are very, very, very thin sheets, so we can bend them this way, and it looks like, indeed, the resulting structure should be stable. So this is a simple molecular bearing, conceptually very straightforward, and if we had an appropriate set of tools, we should be able to build it. Here we have something a bit more complex. This is a planetary gear. This starts to use other elements. It's using silicon and oxygen and hydrogen, but the basic idea is still there. It is a complex, three-dimensional structure, which presumably is inaccessible using today's chemical synthetic methods, but which we think we could build once we had an appropriate set of tools. Now, the particular set of tools I showed you, because they only deal with hydrogen, carbon, and germanium, would be insufficient to build this structure. This structure would require an additional set of tools and a fair amount of complex analysis, but we believe that the same conceptual framework would work like a charm. So something like that. And then as you move on up the scale of complexity, there's no particular reason you couldn't build a robotic arm. Now, this robotic arm has not been designed in atomic detail, so you don't see the locations of every atom. The primary reason for that is that it has on the order of a few millions of atoms in it, and the design effort by itself would take significant work, and no one has walked up and said, here's a check for the sum of money that would be required to do a careful computational design and modeling of a robotic arm. Nonetheless, the basic principles are well understood, and we have a high degree of confidence that if someone said, yes, we want to have a detailed design, we could in fact make a design of a molecular robotic arm, and that particular robotic arm is perhaps 100 nanometers tall or so, so it's very small. We could go ahead and design such a thing, and then if we had an appropriate set of molecular tools, we could use those tools to build a structure like this. And in addition, a molecular robotic arm.